Welcome back to my game development journey. In this first devlog, I will show you how I created power grids for my game. After all, it wouldn't be a proper builder game without cool energy network. I'm using Dijkstra algorithm. Why? Because it's efficient at finding the shortest path in the network. You could use alternatives like the A-star algorithm, but for my game, Dijkstra's algorithm is the best fit. What is Dijkstra's algorithm? Dijkstra's algorithm is an algorithm that finds the shortest path from a starting point to all other points in a network by assigning a cost to each point and tracing paths based on the lowest costs. Let's see how I implement this algorithm in my game. I have a solar panel, which is an energy source. I call it the source. I also have a time tracker, representing an energy consumer, which I call the user. The goal is to transmit energy from the source to the user through a power grid, a network of transmitters. If I use a basic approach where transmitters connect to any others in range, it results in a messy and inefficient grid. Another approach could be to only connect to the nearest transmitter in range, but this might cause energy from the source to fail to reach the user. That's why using a pathfinding algorithm is so helpful. It ensures energy flows efficiently and avoids the issues. In my game, I assign names to transmitters based on their role in the power grid. Transmitters connected to the source are called start points. Transmitters connected to the user are called endpoints. All other transmitters in between are called links. Dijkstra's algorithm in my game has two phases. Phase 1. Find paths. Start by setting the cost of the endpoint to 0 and all other transmitters in the grid to infinity. Calculate the cost of each transmitter, working outward from the endpoints. Whenever we encounter a start point, we store it in a list for later path tracing. This transmitter is a start point, so we add it to the list of connected start points. This process continues until there are no reachable transmitters left. Again, we encounter start points, so we add it to the list of connected start points. Phase 2. Trace paths. Using a list of connected start points we stored earlier, reconstruct the paths. If the list is empty, it means no available paths can be constructed. We start tracing from this start point. While tracing, we only add transmitters that have the lowest cost and are nearest to the current transmitter being inspected. We are inspecting this transmitter. There are 3 transmitters in range, but we only connect to the transmitter with a cost of 2, as it's the lowest cost transmitter. Next, there are 4 transmitters in range, but we only connect to the transmitter with a cost of 1. The path ends when we reach a transmitter with a cost of 0, meaning we've reached the endpoint. The process continues until there are no stop points left in a list. The pathfinding process completes with 3 possible paths, connecting stop points to endpoints. Now, we can provide energy to the user through these paths. Let's say the user is demanding 5 energy per second. To meet this demand, we activate the shortest possible path and draw energy from the source. For this demonstration, each source produces 3 energy per second. First, we draw 3 energy per second from closest source. This depletes its energy production, so the path connecting this source to the user becomes active. The user demand now drops to 2 energy per second. Since the user still requires energy, we activate the second shortest path and begin drawing energy from another source. This source production decreases from 3 energy per second to 1 energy per second. The path connecting this source to the user becomes active, reducing the user's demand to zero. Finally, the user's energy demand is fully met, and it stops requesting energy. Because the user no longer needs additional energy, the remaining path stays inactive. When energy production or consumption changes, there's no need to redo the pathfinding process, as long as the start points and end points remain unchanged. Instead, we simply recalculate the connections based on the energy demand, energy production, and the existing possible paths. For example, let's add another user to the endpoint. With this new user, energy consumption increases, but since the start points, endpoints, and possible paths stay the same, we only need to recalculate the connections. Let's recalculate the connections. After running a recalculation, we find that one user isn't receiving enough energy and cannot function normally. This state is what we call inefficient power. To fix this, we can add a solar panel to increase energy production. If we add this solar panel to an existing start point, there's no need to run the pathfinding process again. However, if we move the source or user to a completely new location, creating a new start point or end point, we'll need to run the Dijkstra's algorithm again to determine the new possible paths. Let's try moving the new user and new source to different locations. This creates 2 endpoints and 4 start points. For each endpoint, we need to run the pathfinding process separately. Since there are 2 endpoints, we'll run the algorithm twice. Let's start with the first endpoint. First, we reset the cost of this endpoint to 0 and set all other transmitters to infinity. Then, we calculate costs outward from the current endpoints. Each time we encounter a start point, we add it to a list of connected start points. Once the pathfinding for the first endpoint is complete, we reconstruct the possible paths. Here are the possible paths connecting start points to the first endpoint. Next, we repeat the algorithm for the second endpoint. After finding the possible paths for both endpoints, we recalculate the connections based on each user's energy demand. Finally, we successfully provide energy to all users. As you might have noticed, after drawing energy from all sources, one source still has the energy production. So, what can we do with it? We build a battery station to store excess energy. To integrate the battery into the power grid, we treat it as a special type of transmitter. This means it can connect to sources or users, transmit energy across the network, store surplus energy, and even act as a temporary source when needed. Let's replace this transmitter with a battery station. Since the battery is a special transmitter, we need to rerun the algorithm to understand its interaction with the existing power grid. Because the battery can act as a temporary energy source, it also functions as a start point, so we add it to a list of connected start points. At the same time, Since the battery draws energy from sources, it acts as an endpoint as well, requiring us to run pathfinding from it. When drawing energy from the battery, if its storage has enough energy to meet the endpoint's demand, we connect the battery to the endpoint and ignore other paths. Once all users are satisfied with their energy needs, we redirect any surplus energy back into the battery for storage. After establishing connections, we can hide any inactive paths for a cleaner look. Additionally, overlapping connections can be merged into a single line for better visual clarity. To make the connections more dynamic, you could add a flow effect, where the direction of the flow indicates the movement of energy through the network. And that's how I've implemented Dijkstra's algorithm in my game. I hope this explanation helps you visualize the pathfinding process. If you want to use this in your own game, feel free to adjust it to suit your specific game mechanics. At the end of this devlog, I'd like to share some other progress I've made in my game. I've implemented an inventory system that allows players to pick up, drop, and store items. Currently, there are only 2 items, copper and silver ores. This is just the core system for now, but I plan to add more items in the future. The UI I created was pretty basic at first, so I spent some time adding animations to make it look and feel better. I also added a mining feature. Players can now mine resource deposits. However, I haven't created a true gun yet, so the astronaut is currently using an invisible one. Another feature I worked on is the building system. Players can now construct machines, and this system is fully integrated with the power grid I made earlier. You notice that when I place a machine near transmitters, they react to it, which brings everything together. That's what I've got so far in my game. Thanks for watching, and if you enjoyed this vlog, please consider liking and subscribing. See you in the next one.